Good day, students. Welcome to the AP Calc AB exam review. We're going to be looking at the free response questions for 2013. Let's go ahead and take a look at question number one. All right, so number one says, on a certain workday, the rate in tons per hour at which unprocessed gravel arrives at a gravel processing plant is modeled by G of t equals 90 plus 45 cosine t squared over 18, where t is measured in hours and t is between 0 and 8. Or t goes from 0 to 8. At the beginning of the workday, at t equals 0, the plant has 500 tons of unprocessed gravel. During the hours of operation between 0 and 8, the plant processes gravel at a constant rate of 10 tons per hour. Okay, so let's see if we can get a understanding of what's going on here. So initially, at the beginning of the workday, we had 500 tons of unprocessed gravel. Okay, so let's say this is the unprocessed gravel here. You have, this is the amount. Okay, amount, uh, initial amount you had um, at the work site is 500. Now you have gravel being processed at a constant rate of 100 tons per hour. Okay, so there's gravel going out being processed, and while gravel is being processed, you also have gravel, unprocessed gravel, being fed to the site. All right, so how do we represent these two quantities since they're provided to us by rates here? So what you want to remember is your basic equation. Amount or quantity is rate times time. Okay, this is if you have a constant rate. But if we want to use variable rates and infinitesimals and calculus, basically, amount can be determined using the infinite sum of radius times infinitely small in time intervals. So this is basically looking at the accumulation of rate times time for infinitely tiny time intervals. Okay, so this is the expression for amount. It's basically an integral of the rate. Okay, now let's see what's going on here. Gravel goes out at 100 tons per hour, or is being processed at that. So at any time t, the amount of gravel going out is going to be, a of t is going to be the integral from 0 to t of the constant rate at which gravel is going out dt. Okay, or we can just, this is the same thing as 100t, but this is like the fancy way of writing it using calculus. All right, okay, so we're gonna write this using calculus. So 0 to t. So coming in is a much more complicated function. This is a constant function, that's why it's easy. So this is, let's call this out. All right, it's being processed, and then coming in, the unprocessed gravel coming in is given by this variable function right here. All right, so for this one, oh, quick correction. This is supposed to be ds. This is ds. Different variables. Okay. All right, so here, rate coming in, we're going to have the amount. In terms of t, is going to simply be the integral from 0 to t again of this function right here. So basically 90 plus 45 cosine s squared over 18. That's ds. Okay, so that's the rate coming in at any point in time, and then that's the rate going out at any point in time. Okay, so that's just the background, just the setup of what the scenario is. Okay, all right, so let's see. For A, it says find g prime of 5. That's, we have to evaluate the derivative of this rate function at t equals 5. Okay, so g prime of 5, let's use a different color here. A g prime of 5, this is a numerical integration problem. G prime of 5. I'm going to show you how we can do this using the TI-89 and also the TI-83 or 84. Alright, so I have my TI-89 and my TI-83 plus. Now, there are two ways that you can find a numerical derivative. Anytime you're evaluating a derivative at a point and you're free to use a calculator, you want to use a numerical derivative, okay? I'll show you two ways to do it on TI-89 titanium, and there's just one way to do it in the 84 or 83. Okay, so for the TI-89 titanium, you can find the derivative. You find the derivative of the function. The function is let's see what the function is. It's 90 plus 45 cosine uh, t square, t raised to the second power, t square over 18. What was that? The variable for the function is t, okay, comma, okay, and then we close it. Okay, so what this does is it helps you calculate the derivative, all right? So that's the derivative of the function right there. But we are looking for the numerical derivative. So what you can do to hasten the process is you want to evaluate the derivative of this function at t equals 5. Okay, so to do that, you see this button right here underneath the equals slash t equals 5. Okay, so this slash right here basically means evaluate. Okay, so you can evaluate any function at any specified value for the independent variable. All right, so let's see what that is. Diamond enter will give us an approximation. So our answer is negative 24.5875. So this is one way of doing it using the TI-89 titanium. Just you use DDT, derivative button, second function 8. Another way you can do this is by using the numerical derivative function. So you go to catalog and then look for numerical derivative. And that's exactly how you do it at the 83 plus too. So for the 83 plus, you go catalog and then press N and go down to numerical derivative. These are identical functions, but the way it's entered in the TI-89 titanium is slightly different from the 83, okay? So let's do the 89 titanium first. So for that one, we're going to go 90 plus 45 cosine t squared over 18. Close that, and then t, enter. So what this basically does is it just looks for the derivative, okay? But we want it to evaluate the numerical derivative at a value, so can you guess how that will be done? You just simply put the evaluate at t equals what? T equals 5. And when enter, bam, there goes the answer. Negative 24.5874. So if you want to use the numerical derivative or the derivative differentiation function, you still have to put in the evaluate symbol button and then assign the variable to a constant. Alright, so that's how you do it. Now over here, you press enter. The syntax here is slightly different. This one, everything goes in the parentheses, so the function 90 plus 45 cosine t squared. Now x, t, theta, n, they all occupy one button for your 83 and 84, okay? So x is playing the role of t here, so don't let that distract you. So x squared, look at it as t squared, okay? Divided by 18. Close the cosine. Now you want to put the variable for our function is t or x in this case. And then this is where the difference is. Instead of evaluating at x equals blah as done in the 89, you just put comma and put the value that you want to evaluate your derivative at, which is 5. Okay? One last thing. Let's make sure that it's in radian mode. The angular measures have to be in radian, okay? Or else we'll throw off our answer. So this is in radian. This one is in radian. You see the RAD here. If it's not, you go to mode, and then you go down to angle. Scroll down to angle, and then make sure it's in radian. That is extremely important. Alright, so it's in radian, so this is fine. This one is in radian, so that's fine. So enter. Negative 24.58 0.575. Okay, so let's write down our answer to 3 decimal places. G prime of 5 is negative 24.588. Okay, but we're asked to use the correct units here. Using the correct units, interpret your answer in the context of the problem. So we want to remember that this is a rate. Looking for the derivative of a rate, or ddt of a rate, is looking for the rate of a rate. So if this were velocity, what we just found would be the acceleration, the change per unit time of the change per of a quantity. Okay, so let's explain what this means using the correct unit. This is the rate at which the gravel is being poured in or is arriving, the rate at which the gravel is arriving. The gravel is arriving. So what does this minus tell us? It tells us, it gives us a direction. So the rate at which the gravel is arriving is decreasing. So that's what the negative means. So the rate at which the gravel is arriving is decreasing by 24.588 tons. Now per hour is for g of t, but we're differentiating it again per unit time, so per hour, or per hour squared. Okay, if you think about acceleration, remember acceleration is going to be something like meters per second square. Velocity is meters per second. So this is just like acceleration. So tons per hour, okay, or per hour square. So this is a better way of writing it in word form. Okay. All right, let's shift our attention to the letter B. All right, let's take a look at the B part. It says find the total amount of unprocessed gravel that arrives at the plant during the hours of operation on this workday. So what is arrive? Arrive means the amount of gravel coming in. So we're just focusing on this function right here, the amount coming in. So what's the total that comes in during the hours of operation? So to find the amount that comes in, all we're just simply going to do is we're going to do the accumulation on the rate at which unprocessed gravel arrives. Okay, so we're going to look at, it's going to be um, a is basically going to be the integral from 0 to 8 of this function right here, which is basically 90 plus 45 cosine it doesn't really matter the variable that we use. We can, since we're using s, let's just stick with s. So it's going to be times s squared over 18 ds. All right. So remember we talked about it earlier that this integral formula helps us calculate the total amount of gravel that comes in at any point t after 0 seconds. So this is basically what we're going to be evaluating. I'm going to show you how to do this with both calculators. This definite integral right here. So let's start with the TI-89. Now, let's see. With the TI-89, you have direct access to your integration function on your home keys. So let's go ahead and do that. Second function 7 is the integral symbol. And then we're going to enter the function 90 plus 45 cosine, let's just use t. It doesn't matter what we really use, so let's use t squared over 18, and then the variable of integration is t, or s, whatever you want to call it. And then the next thing in the syntax is the lower limit of integration, which is 0, to the upper limit, which is 8. That one enter for an approximation. 825.551. So this is the total amount of unprocessed gravel that arrived. Okay. Now let's go over how to enter this in the TI-83. The same procedure is applicable to the 84. Okay, so we have what we're gonna do here is gonna look for fn int. So let's go to the catalog. For the catalog, second function 0. Fn int helps you calculate the integral. So we're doing numerical integration here. So press F to jump to the F menu, and then function integration. The syntax is exactly the same as this one. So 90 plus 45 cosine let's use x squared, variable doesn't really matter, divided by 18. A variable of differentiate integration is x, lower limit of integration is 0, all the way to the upper limit of 8. Close that, enter. 825.551. Okay, so that's the total amount of unprocessed gravel that arrived during the work day. So let's write it down. 825.551. Okay. So let's also indicate the units. Tons. That's the total amount of gravel that arrives. Now let's look at part C. It says, is the amount of unprocessed gravel at the plant decreasing or increasing or decreasing at t equals 5 hours? So we have you have gravel coming in unprocessed and gravel going out. Okay, so if the in is greater than the out, then it's going to be basically increasing, okay, because it's not going out fast enough. But if the out is bigger than the in, then it's going to be decreasing because it's going out faster than it's coming in. So think about your bank account, for example. If your rate of saving is lower than your rate of spending, what's going to happen to your balance? It's going to keep falling because you're spending too much. All right, but if your saving is much faster than your spending, then your amount is going to be, the amount of money in your bank account is going to keep increasing. Okay, that's just a way to look at it. So what we're basically doing in portion C is comparing these two at t equals 5. Okay, if this is bigger, then it's decreasing. If this is bigger, then it's increasing. Okay, so to figure out the amount that's going out, that's being processed at t equals 5, that's easy, right? Because it's constantly 100. So what we just have to bother with is what is the rate at which gravel is coming in at t equals 5. So to find that, we're just gonna, so let's write down the plan for solving this problem. So for part C, all you're simply doing is you want to compare G of 5, which is the rate coming in, with 100. Okay, how does these two compare? Okay, so let's find G of 5. G of 5 is what you get when you input 5 into your function. So let's go ahead and do that. Alright, so one trick I'm going to show you is by storing constants in a variable. So let's do that with the 89 first. So let me take everything away. I just want to just isolate the function. So this is the function right here. Okay, now if I want to evaluate this function at t equals 5, I can store 5 in t. So how do you do that? You press 5 and then you store it in t. Enter. And then let's call up the function. Diamond, enter. And this is the rate at which gravel is coming in at t equals 5. Alright, so by storing constants in your variable, you can evaluate functions at different values. But when you're done, don't forget to clear up your variable. For your TI-89, if you want to clear up your assigned variables, you just simply press F6, which is second function F1, and then you hit clear A to Z, and that takes out the assignment that you made to any variable that you did. Okay, so don't forget to clear your assignments so you don't ruin your other answers. Okay, so this is the way to evaluate a function quickly using the TI-89. or you can basically type in the whole expression. You know, if you want to waste time, you could do that. All right, let's take a look at the TI-83 or 84 plus approach. So for this one, the same idea. I can store 5. I can store that in X. Enter. So 5 is already stored in X. If you want to check, you just press X and press Enter. You see X is now 5. What I'm going to do is press second function entry. That gives you the previous entry again. That gives us the next entry. I want this one, so let's do it again. That gives us that entry. So let's take out all the stuff we don't need. I just need the function, so delete all that stuff out of there. Go up, delete that. Okay, let's see. Enter, bam. There you go. All right. So by storing variables and constants, constants and variables, you can evaluate functions real quickly instead of typing this, long process. It takes too much time. Okay, so we can see that g of 5, the rate at which Gabo is coming in, is equal to 98.14. What was it again? Let's see. 14076, and that is less than 100. So the rate that's at which gravel is coming in is less than the rate at which gravel is going out. Then that means it's going to be decreasing. Okay, so at t equals 5, unprocessed gravel is coming in slower than the constant rate of processing. The constant rate at which the gravel is processed out. Okay, it's processed out. So so the amount of gravel at this time is decreasing. So hence the amount of gravel at t equals 5 is decreasing. Okay, because out is bigger than in, is decreasing. So that's that. Okay, let's take a look at part C, or part D. Part D I meant to say. Okay, so it says, what's the maximum amount of unprocessed gravel at the plants during the hours of operation on this workday? Justify your answer. So maximum amount, we know that the amount of gravel that's present constantly changes. Okay, if you're looking at the total amount, we have to consider the interaction between the amount you had initially, the rate of gravel coming in, and the rate of gravel coming out. Okay, so let's look for the expression for the total amount of gravel at any time t. Let's call that A of t. So the total amount of gravel at any time A of t is given by the total amount of gravel you had initially, plus we can combine the rate of in and out, okay? From 0 to any arbitrary time t of g of s. This is g of s represents the rate coming in minus the constant rate going out. This entire expression ds. Okay, we're using an integral to represent these two because they're variable rates. Now, how do you find the maximum or minimum, the extremal of a function? Since this is on a closed interval, to find the maximum, we have to consider the endpoints and the critical points, okay, where the derivative is 0 or non-existent. So we have our endpoints, and then we need to find our critical points. So how do you find the critical points? You find critical points where a prime of t is equal to 0, or a prime of t does not exist. All right, so if you take a look at this function that we're dealing with right here, it's a trig function. It doesn't appear to have any weird things happening. Hopefully not. To verify, we can take a look at our calculator. You can just graph the function to see if there are any violations. I don't see any violations happening here. So we have a nice function that's smooth and continuous. So we're just going to look for when the derivative is equal to 0. All right. So let's go ahead and do that. To find when the derivative is equal to 0, we'll just simply differentiate this function right here, and then set it equal to 0 and solve. Okay, so we're going to find a prime of t is going to be the derivative d dt of this entire equation right here. Okay, 500 plus the integral from 0 to t of g of s minus 100 ds. Okay. Okay, so if we differentiate this, is pretty easy to differentiate. If you differentiate this constant, it goes to 0. And then in this case right here, we're going to use FTC part 1. If you evaluate the derivative of this integral, all you end up doing is plugging in t into this, into the function right here. Because when you evaluate this antiderivative at the lower limit, when you differentiate a constant, this piece is just going to drop off. Okay, and then this is a constant function, so when you integrate the derivative of a constant function, you end up with a constant function. So at the end of the day, this derivative sends this to 0, this derivative cancels out this integral, and you just plug in t here, you have g of t, and then if you integrate this and differentiate it, you just be left with what you started with, 100. So this is a derivative, set it equal to 0, and then you solve that. Okay, so let's go ahead and do that. Alright, so all we're just going to do now is find the zeros of this function right here. So we're going to graph 90 plus 45 cosine t squared over 18 minus 100. And then we'll look for where it intersects or crosses the x-axis, okay? So that's what we're going to be doing, looking for the zeros. All right, so let's enter it in the TI-89 titanium. Now I'm going to make a mistake here. In my entry, let's see if you can catch what my mistake is, okay? So I'm going to enter the function. It's going to be, let's see, 90 plus 45 cosine t squared over 18 minus 100, okay? Enter. Let's check it to make sure it's right. 90 plus 45 cosine t squared over 18 minus 100. Good. And let's graph it. Now you notice we have a horizontal line. It never crosses the x-axis. So basically this is telling us that there is no solution. So let's go back. There's something wrong with our entry. Can you see it? All right, let me highlight the function, press enter. You notice here our independent variable in the graphing menu is x, and I'm putting a t here, so there's inconsistency with our independent variable, so that's why my graph is coming out incorrectly. So this t has to match the independent variable here, so this has to be an x. Okay, press enter. Now the calculator can do a calculation. So let's see what it tells us. Graph. Oh, that's more like it. All right, so let's see. This is 1, 2, 3, 4, 5, 6, 7, 8. So this is the only zero that's in the domain of the problem between 0 and 8. So let's go ahead and find out what that is. So we're gonna use F5. We're gonna use the 0 option. Okay. So 0 is menu 2. So it says lower bound the point to the left of that C. The points to the left of the 0, let's pick 1, 2, 3, 4, so let's enter 4. 4, enter. See the arrow points to where the 0 is located. Upper bound, the point to the left of it, let's use 6. I mean, a point to the right of it. enter, and it tells us that the 0 is located at 4.923. 4.923. Okay, so that's basically the critical point that we're looking for. So let's go ahead and write that down. Critical point is t equals 4.9234. Okay, so that's the critical point. The procedure for the TI-83 is exactly the same thing. You just press Y, and then you enter the function. What's the function again? 90 plus 45 cosine x square over 18 minus 100. Okay, let's make sure it's correct. Enter graph. All right, so how do you calculate the zeros here? How do you calculate the zeros here? Where did my calculator go? Okay, there it is. Okay, so how do you calculate the zeros here? This one, let's see. The calc menu is the same as the math menu here for the graphing window in the TI-89 titanium. So second function trace will give you the options that you can calculate in the graph window. So we're looking for 0, option 2. It says lower bound we used 4, enter. Upper bound we used 6, enter. See where those 2 points arrows are pointing to where the 0 is located, and it says guess. Yeah, guess. Answer is 4.9234. Okay, so there goes the 0. And in the context of this problem, that's a critical point. So what we're going to be doing now is we're going to be evaluating our function at these 3 points. Whichever one yields the maximum output, that tells us the maximum amount of unprocessed gravel at the work site during during the entire workday. Okay, so let's go ahead and set up our table. We have 3 t-values to check. Remember the procedure for finding your extrema, your max and min, or in this case the maximum, is you want to look at your endpoint and your critical points. Okay, so t and the amount. All right, so we look at the original amount, the starting amount, how much gravel was there before processing started. There was 500 tons. We remember that. So um, if you are not sure about how that works, you can look at the original formula, that the function that we created before. Let me set it up for you. So it looks like this. So at t equals 0, amount a of 0 is basically going to be the integral from 0 to 0 of I don't have the integral first, so it's going to be, starts with 500. Remember the formula we came up with. So a of 0 is equal to 500 plus let's try that again. 500 plus the integral from 0 to 0 of the rate at which unprocessed gravel comes in minus the constant rate at which processed gravel goes out, ds. Now you see this right here? They have the same limit, so this entire integral expression goes to 0. So you just left with 500. Okay? Now the next two we want to evaluate is when t is equal to 4.923, and then the other one is where t is equal to 8. Okay, so for this one we're going to be looking for a of 4.923, which is 500 plus the integral from 0 to 4.923 of g of s, the original function. You don't have to write this over and over again. You can just plug it into your calculator, but I'm just going to show you what I'll be entering. Okay, so g of s is 90 plus 45 cosine let's use s, minus 100 ds. Okay, that gives us the amount at the critical value, and then A of 8 is the amount at the end of the workday, which is 500 plus the integral from 0 to 8 of 90 plus 45 cosine s minus 100 ds. All right, so we just basically plug these two integrals in our calculator. All right, so let me show you how to enter this with the TI-89 titanium. So we're gonna go do 500 plus um, the definite integral, second function 7, integral of the function, which is 90 plus 45 cosine. We can use whatever we want. Let's use t. Okay, cosine t. Well, yeah, cosine t minus 100. Okay, variable of integration is t. Lower bound is 0 all the way to 4.923. Close that. Enter. Let's see. Okay. All right, so I made a mistake here. Oh, in my intro, I made a mistake. So what was supposed to happen here is we're supposed to have this variable is not just s. It's supposed to be s squared over 18. Let's fix that real quick. That's when my answers are off. So it's going to be s squared over 18, and then s squared over 18. Okay, those are the formulas we came up with before for a of t. Okay. All right, so let's apply that correction. So it's not just t, it's t squared over 18. Okay, so t squared over 18. Sorry about that. Oh, 635.376. Okay, so same procedure for the other calculator, 635.376. And then if you want to integrate all the way to 8, you just simply take this out, put an 8, and then enter. Wait for a second, it's calculating. 525.551. Okay, so 525.551. Let's write that down. 525.551. So when do you have the maximum amount of gravel? So actually, you ask for what is the maximum amount. So the maximum amount of gravel, the maximum amount of gravel for workday is 635.376, because that's basically the highest amount considering the fact that we evaluated the endpoints and the critical point. The critical point basically one here, okay? Tons, and that's that. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel for updates to other cool clips such as this. And please post the comments to let me know what you think about this clip. More clips can be found on math.serve.com/calculus. Thanks again for watching, and have a wonderful day.